good afternoon or good evening for this global conference, depending on where you are. My name is Rakesh Dodeja, and I'm going to talk about how to deploy containers to build IoT solutions with microservices for fog and edge nodes and in the cloud. And a brief introduction about me. I'm a principal engineer and a chief systems architect at Intel, working in Intel since July 2000. Previously, I worked at HCL in India till 99. I graduated with my master's in controls and instrumentation in IIT Bombay. And previously, I did my BTech in electrical engineering in 1980 from IIT Varanasi. I've been working on IoT space. Earlier, it used to be called embedded UM since 2010, and developed and delivered and showcased complete IoT solutions for home, office, building automation, industrial, energy, etc. And being at Intel. So I love to work on Linux, app level, security, manageability, and networking. So I'm going to share my screen now. I have a lot of content. We'll talk about the solution requirements for IoT solutions. This is a lot of content, and we'll quickly get into the nitty-gritty of the discussion. I'm going to talk briefly about containers, so what they are, what they can be used for, what kind of problems they can solve, and what are the popular container frameworks, and history of containers, because now they have become very popular, so we need to know how they kind of evolved. Then I'll shift my discussion specifically on Docker containers, the architecture, some tutorial and Docker files, how to build a Docker container, additional resources on containers, doing development with Docker, building, shipping, and running complete solutions, and then how to orchestrate the solutions using available frameworks and tools, and also talk about container management tools. So what is really happening is all the IoT platforms are being built, and by various vertical teams, various types of solutions are being built, and solutions are becoming available, and they're deploying solutions. But developers have their choice of operating systems. Everyone does not like Ubuntu or Red Hat or whatever, Wind River Linux, or even Windows, right? Someone would prefer Windows, someone would prefer Ubuntu, and so on and so forth. So they will do the development of their solution in their preferred operating system, and when it becomes necessary to deploy the solution, the customer of that solution may not have that operating system. So you need to make available their solution components to run across a variety of operating systems. And virtual machines were being used and are still being used, and containers have become available, which kind of help solve this problem, right? And we've kind of realized that to be able to scale the solutions, you need to have modular architecture, right? And they need to be deployed across the infrastructure. You want to have your solutions, run in the cloud. There is a cloud component, and I'm sure a lot of you have heard the new term called fog. So there's a fog component of your IoT solution. And then you have edge nodes, right? So there are various requirements of IoT solutions. There are sensors at the edge which collect data. Then there are control actuators which kind of turn things on and off. So you do the data abstraction by pulling the data out of the sensors, clean it up at the edge nodes, and then send it to the fog node, which may be connected to the cloud. On the fog nodes, you may do more processing of the data, kind of extracting some of the insights, doing analytics on the data. And then you want to make sure that data is governed properly and protected. So all these requirements, a big list of requirements are there for your IT solutions, and you may have to optimize your solution for cost, and then you want to make money out of it in the long run. So there is an OpEx cost when you operate your systems. There's a cost there, so you want to optimize for both CapEx and OpEx. Of course, you will make money only when your solutions are scalable, right? So you are really gearing for building a solution which will scale. And during the life cycle of the solution, your IoT service, you want to make sure that you can update your solution. You can add new capabilities, new features. So, and there may be bugs found. You may want to, be able to quickly fix the bugs, right? So these are at a high level the requirements of IoT solutions. And to be able to address this, as I mentioned earlier, right, containers are kind of becoming a nice way to virtualize the distribution of your solution, right? So we want to understand what containers are, what benefits they provide, and how containers can come and help us, right? So let's understand what is a container, right? So container is basically a method to isolate your application from some of the variances of the operating system, right? You may have an application built as I mentioned earlier for Ubuntu, but you may want to run it on Red Hat, right? So how do you do that? Either you may have to kind of modify, port it for running on Red Hat, or run a VM, or package it as a container. So what is inside a container, right? So you have a application code or a binary, right? You have the associated libraries and some dependencies on the operating system. So you package the container, you package your application inside the container, and then run it on the host OS on a container framework. And we'll talk about some of those frameworks available. And this packaging capability of an application inside a container actually now makes it portable. So you can run the container on different variety of operating systems, right? A container built with Ubuntu libraries, and a binary which runs on Ubuntu libraries can run on Red Hat very easily. And this capability of running one container or maybe more than one container is done and managed by the framework, which is the container framework. We also call it a container engine. So there are varieties, different types of containers. You have operating system containers and you have app containers. So operating system containers really have additional capabilities. They can run multiple processes inside the container. For example, a MQTT broker, an HTTP service, a systemd service, SSHD, blah, 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 right? So you can choose whatever you want to run inside a container. So since it is using kind of a ability of a VM or a main OS, right? So these are called OS containers. But when you want to kind of fine grain the level of abstraction inside a container, you want to just run one component of an application, then we call those app containers, right? For example, if you want to just run the MQTT service inside a container or MQTT broker inside a container, we call it an app container. So the same thing on the left, you can actually break down as a set of app containers. You probably achieve the same functionality. But we'll see what flexibility these offers as we go along. We also want to compare what containers offer. How are they better than VMs or versus the legacy monolithic applications, right? If you today or in the past, solutions have been built and developed, and for example, if you run your application on your laptop, take an example, a Word application or whatever, it's a monolithic application. It does everything, right? It's a self-contained application. Of course, it uses the host libraries, user space libraries, and the OS capability, and then runs on the platform. And you can run multiple applications on the platform, right? So that's the legacy way. And then when we went to data centers and in the cloud, we wanted to run a lot of applications, whether they are services or whether they are analytics capabilities or whatever. We wanted to isolate them, so we took help of virtual machines, because we had capable platforms, a large number of processor threads or processor cores, large amount of memory, and so on and so forth. So we wanted to take advantage of that, but each of these applications did not need so many, and we wanted to scale, so we put them in virtual machines. But then virtual machines again are resource heavy and consume a lot of resources. They have boot up time, startup time, stop time, and all that. So and when containers became available, we realized that containers are actually much lighter. They are self-contained and give you benefit of being lightweight. They can run inside a VM and run on the native machine. And and we'll see the benefits of containers. How you'll realize that the lightness of the container can actually allow you to run multiple containers inside a VM. Let's look at that in the next file. This is just the same, comparing a VM versus a container here. So you have a hypervisor, and on the hypervisor you have multiple guest OSs, and then each of the guest OS you have some binaries, and then you have an app, right? So on a host platform you can run a lot of VMs, right? But when you actually want to run containers on the same host platform, you can use a framework. For example, I'm showing a Docker engine here, and on top of it you run same set of libraries and apps, right? So the hypervisor goes away, a container framework comes in here, right? And it allows you to do the same thing. But you will see in my later file that you can actually run the same set of components which you're running natively on an OS inside a VM also, right? So here I'm going to be more descriptive here. You can kind of read through most of it, but let's talk, right? So containers, you can, when you're building your containers, you can limit the amount of memory they use. You can limit the amount of CPU threads they use. You can choose the libraries they use, and they are independent of the host kernel. So you can run on one host or the other host, one Linux version or the other Linux version. Only the kernel is what is used by the container. Rest of the resources are all local. The libraries are local, right? You can package one or more applications components inside the container, as I mentioned earlier. As I also mentioned that you can have containers running on a variety of operating systems. And containers can also run on, Linux containers can also run on Windows platforms, because there are abilities to run VMs on Windows platforms, and inside VMs you can run a Linux VM, and then you can run Linux containers. Windows also supports native Windows containers on Windows servers and Windows machines with Hyper-V. So there are two types of containers, and they have different level of capabilities. So the advantage, as I mentioned earlier, you have startup time advantage. They run much faster. The startup is much faster as compared to VMs, because there's no boot of the OS needed here. The OS is already booted. With the framework, you just instantiate the container and load the libraries and just run the container application inside the container. So it's pretty fast. And also there's an improvement in performance, because the libraries and the OSs don't have to do two levels of negotiation of the OS. One in the virtual machine OS, and then second in the host OS. So that benefit also improves performance. And the structure of containers actually allow you to reuse the resources, and we'll see how that happens. So IDC and few others did surveys on containers. So some of the benefits are listed here, and some in the next slide, right? So not all VMs are being replaced today. Containers are running inside VMs and natively in the cloud. Some have to run native in the cloud because they really want to scale the applications, services in the cloud, and you just keep on instantiating a lot of instances of, for example, an HTTP service, a lot of, on demand, you can keep on scaling. There are a variety of container technologies, and we'll talk about it in a later file. Most common OSs support containers, right? And as I mentioned, Windows containers are also becoming very popular, and there are at least one framework I know which is very popular with both Windows and Linux containers. And as we talk about microservices and distributed IoT solutions, we want to be able to run our containers not only in the cloud, but we also want to run them on fog nodes and edge devices. So we'll see some of that. So as we already talked about it, we can package app once in a container and deploy across multiple operating systems. And a company like Intel or other IoT solution providers can leverage, containers across various verticals. So some of the, for example, the pub/sub architecture typically an IoT solution will have a broker, MQTT broker kind of service, right? So you just build that container which runs the MQTT app, and you can reuse across various verticals. Of course, you benefit from the fact that everything is common here, so validation cost goes down, right? And it becomes a kind of a common mechanism, not only for building your solution components, but even the tools can be built inside containers, right? I'm posting a link here, and you'll see when you get the slides. You can click on the link and you'll see that how a Joule SDK can be built inside a container itself, in a Docker container. We can package the legacy app like quickly. If you really don't want to port the whole app, you can package all the components of a legacy app inside an app in a OS container, right? Tools, manageability agents, security components, all can be packaged inside containers. And we'll see how quickly, when you have your continuous integration, continuous delivery, OpEx, DevOps infrastructure, you'll be able to develop, validate, deploy, ship, and deploy your containers. There are still some limitations on containers. You really cannot, like, for example, some of the security requirements on the host platform, secure boot, I don't believe can be solved with containers. You still need to manage that at the OS level, at the host level. There may be additional, resiliency problems with containers, right? If you have a unvalidated, poorly validated app or an app component inside a container, which can cause a kernel panic, then the whole platform goes down, right? So you may want to put your application initially in VMs, so to complete your robustness testing and all that, and ensure that you are stable and reliable and ready to go into production, and maybe even launch a VM in production and multiple VMs to keep your availability high, and then maybe make them native to better scale and better improve performance, so that this risk is kind of covered and mitigated. And then, like VMs, you still need to manage your packages, right? You want to have it available, deployable, a repository is required of containers. You want to secure them, right? And as I mentioned earlier, also security is not completely comprehended. There's still, solutions and capabilities evolving. I'm mentioning a company here which is kind of built some capabilities on how to secure containers and how to keep containers up to date, because bugs keep coming in. P-certs keep coming in. This library has this vulnerability, and so this company can actually monitor uh, your container contents, and it can actually keep a database of how the bugs are kind of being reported and vulnerabilities are being reported. And if you have a container which actually has this vulnerability, you can actually configure it to not run, right, or stop running if you find a vulnerability. Let's spend some time understanding a brief history of containers. There is a lot of content mentioned here, and each of these is a link. So, you really don't need to spend time finding all this. You can just click and go, and once you get the files, you'll be able to click and go to these information sources. They're all web-based, and they're, as of today, they're current. I can't guarantee that same links will work in future, but there is a lot of information. It really started long back when Cloud Foundry began using containers. They had a framework called Warden. And then .cloud, which that link doesn't work anymore, so I removed that. But Docker really evolved out of this as an open source project, and now it's a commercial company. And today, each of these service providers, Amazon, Google, and few others are all deploying their solutions and services as containers. CoreOS became available, and it's a very lightweight OS, Linux OS distribution, which is actually optimized for clustering and for scaling web deployments. For deploying and managing and securing solutions using containers. Canonical, company which has the Ubuntu distribution, has alternative frameworks for containers called LXD, which has a very lightweight VM and runs containers inside VMs. So it takes advantages of the isolation provided by VMs and benefits provided by lightweight and quick deployment of containers. CoreOS also created alternative container framework called Rocket, and that's also pretty popular. Twitter is using their own framework for containers called MesoS and Marathon. And Google is rallying behind Kubernetes, so I'm sure everyone is pretty familiar with Kubernetes. And even Microsoft has now partnered with Docker and is now supporting Docker containers, and both the Windows Server-based containers, which have the full Windows kernel inside the container, and also the Hyper-V containers. So the discussion now, I'm going to switch to more on Docker, discussion, because I understand everyone is kind of very keen to understand how Docker works and what is Docker and what kind of containers they have. So let's go look at what is Docker, right? So Docker is a framework available from this company called Docker, right? And Docker container is a lightweight, it's secure, helps you to scale quickly, easy to integrate. It's open source. They also have a enterprise version which is licensed, and it's a service, so you have to pay for it. You can configure your servers, applications, pick your OS, OS type, Linux or Windows, a variety of Linux, right? And tune and install your binary inside your container in a Docker container once, and then you should be able to run it across a variety of operating systems. So more details of Docker is available on the link I've provided. It's an open platform, as I mentioned earlier, for building, developing, deploying, shipping, and running applications inside containers. And it has all the benefits of containers. It kind of isolates your application from the infrastructure. Many containers can run on a host. and each can have a different component of an application, right? You can build your application with containers. Typically, your application will have a connector to the cloud, or connected to the database. Your application will have some compute binaries for analytics purposes. There would be pub sub capabilities to publish your data. There would be, multiple applications running, so synchronization capability, locking capability, and all those stuff. It's the broker, and all of those components can be packaged as containers, and you can build your application as multiple containers, right? And each of them can be lightweight and independently managed. And what I mean by managed is you can actually start and stop the container without starting and stopping other components of this application. So the whole application does not need to be brought down or teared down if you want to update. You just need to update one component. Of course, you need to be able to drain the pubs up data flow happening to that component of the application before you shut it down and start the updated version. But the architecture of containers allow you to be able to build your applications which can be easily updated. You really don't need to bring down your whole system to update an application. So as I mentioned, containers become units of this, package units for distribution of testing, deploying of your application and its components. And it kind of makes your CI/CD pretty agile, right? So multiple teams can work on independent components at their independent speeds. Releases can be independent and really help you build your solution as a microservice. So we'll see how that can happen. But let's understand more about Docker, right? So Docker Engine is a client server application. The server is called Dockered, and client is the command line interface called Docker. It uses REST APIs to talk to the server and the client talk to each other using REST APIs. And the framework can be used to manage containers, images, data volumes, and networking. So this kind of illustrates the advanced features of the Docker engine, right? There is something called swarm mode, Docker swarm, and we'll talk about it later. It can help manage multiple instances of platforms or cluster of nodes, and each node can run, an instance or one or more of instance of containers, right? So you can manage the keys and secrets. You can have TLS sessions between containers or between nodes. You can manage your certificates using certificate authority. You can manage your volumes. You can balance your load. You can discover your services, additional plugins. There's a container runtime. You can have distributed store. So a lot of capabilities are offered by this advanced capabilities are offered by this Docker engine. It is powerful yet simple and has built-in orchestration. As I mentioned, it allows you to have different variety of networking capabilities on your containers, host mode, NAT mode, and so on and so forth. So container platforms, as I mentioned earlier, allow you to have portable workload, and Docker allows you to do that. Docker containers can run on laptops, physical machines, virtual machines. And since it is pretty lightweight, we can actually have the Docker framework run on a, Raspberry Pi class of device, or a, Intel Atom class of device at the edge. And on top of this framework, you can run your containers. So you can actually break your application into multiple containers and run on an edge node. Of course, fog nodes are more capable, and you can run multiple VMs and multiple containers inside VMs on fog nodes. And today, containers are being used in a big way in cloud nodes. and in a cluster of nodes. So really, to be able to manage your distributed nature of your application, you can run and orchestrate your application across the infrastructure. And this helps you really make your application pretty responsive, scalable, uh, because you can quickly move workloads between various nodes in the cluster, between cluster of nodes at the edge, in the cloud, in the fog, across from cloud to fog, to the edge, and reverse. So you can really move your workloads. And containers really become cost-effective alternative to hypervisors, right? Once you are kind of confident that your container is robust and doesn't cause any problems, you can move it out of the VM and run natively. And it's pretty good for dense deployment, right? You can actually run a lot of containers, because if your process needs just one thread and you're running on a multi-core, multi-threaded machine, you can run multiple containers, each consuming one thread of process, right? I already mentioned you can deploy across the infrastructure, edge, fog, in the cloud. So we are now coming towards the uh, orchestration aspect of the discussion, right? So as we understand, because of the lightweight nature of the containers, we can really build our solutions, compose our solutions with multiple containers, and we can move them across. We really need some tools to be able to do this orchestration. And I think one of the future files talks about it. Let's quickly hit that, right? And before we do that, I just want to hit one more file, which is talking about the architecture of the end-to-end architecture of Docker, right? So there is a client component we talked about, and the command line commands can be used to build, pull, run containers, right? The host runs the daemon. So client and host could be actually across nodes, right? You don't need to be on the same node, and they could be connected. And the containers are running on the host. You can have images locally or remotely. So that's why you can see the container images can be stored locally or cached locally for reuse purposes, bringing up and down the containers quickly. Or they could be in the remote registries, like Docker Hub, for example, where you could actually have some base images, and you can build your application specific images either on the host, or you can store your your application specific images locally or in the remote, on the remote hub. So it's pretty versatile capability and pretty popular, and everyone likes it. I have more links here to get started with Docker and how to go about it. And then I also have a couple of Docker files as examples, because some of these capabilities I'm showing in these Docker files are more for the OS containers where you want to put multiple application components. But very easily you can create a lightweight Docker file by not doing some of the stuff I'm showing here. This is really showing how to really package a Wind River IDP image inside a container with enabling the systemd services and running inside a enterprise which has proxy. So a lot of capabilities of a container are kind of put in this image, this Docker file, right? So you need to use this to build an image, and I'll talk about the steps a little bit later. This one is another example of an Ubuntu image of a common named data networking daemon, which is an open source component. So this talks about how to build that, binary inside your container, and then run it as a systemd service, right? These are some of the steps which you may use to install and build and deploy a container. Right? You need to install Docker on your host. You need to create a Dockerfile. Some of the examples I have provided. And the OS container libraries can be pulled from a Docker Hub, or you can build from a tarball. Add additional packages which may be needed for your component or for your application component. If you need systemd services, you can enable it inside the container. And after you establish your entry point, you can run your container to test it. And then once you've done your validation, you can distribute it, ship it, deploy it, run it. You can also build a complete CI/CD infrastructure to update it. Additional resources about how to develop apps, native apps. There are new capabilities like multi-stage builds to make your images much lighter. So your build portion can be done one time, and then you deploy your images which much lighter. Manage applications using volumes and mounts. Using the Swarm service, how you can scale your app. And then additional details about best practices. You can actually build your application using your choice of programming language: Java, Node.js, Ruby, .NET, and so on and so forth, right? And this is an illustration of your end-to-end flow, right? Develop, validate, and release. More in the development phase. If you really want to completely take advantage of the end-to-end capabilities, build, secure, and store images locally in on-prem or in the cloud using Docker Hub or your own private registry. And depending on the type of components your end-to-end solution will have and the services they have, you can have all these components managed through Docker, right? So you can see how much of reuse can happen across your cloud components, your provisioning service, your customer portal, developer portal, remote attestation capability, device management capability. You probably need all of these capabilities to have a complete end-to-end solution. And your developers can push build these components, validate them, and then push them to deployment. And when you really want to move your capabilities across the infrastructure, you add the orchestration capability and go from there. So here are some of the orchestration frameworks and tools. I'm not going to go into deep of each of these because each of them is a topic in itself. I think one of them was talked about in one of the previous calls. But the details are here, and you can try and learn about each of them. And I think that's my next file is my last file where we talk about management tools. And again, there is a lot of information here. Feel free to go over each of these. Each of these links should work. So I'm going to now switch over to question answer. Let's see if there are any questions. One question is how gateways and fog nodes are different. Before fog acronym came into picture, compute nodes were referred to as gateways, data center. Yeah, so gateways typically could be Atom or ARM-based devices. Today, you get gateways which are up to quad core, Atom-based or ARM-based devices. Raspberry Pi Rev C is a quad core device also, right? So those are still known as gateways. Fog nodes are more capable, right? So there is an Intel fog reference design which is core and can be even up to Xeon based. It's more of a capable platform and can support FPGAs. So that's the difference between fog and edge nodes. Can a developed Docker app hardware acceleration, graphics engine, or FPGA accelerator? Yeah. So I think one of the previous presentation talked about that. I think Intel Docker or Docker Intel is that, and it talks about how to, access these capabilities. Typically, there is a driver for each of these capabilities on the host OS. There is a mechanism to enable the device driver interface to the container, and using that, the application and the libraries inside the container can access, whether it's a graphics engine or an FPGA. The next question is, can you give a use case scenario how this solution is in the field and what are the personas involved? So I'm assuming you're talking about it, right? Where you have a end-to-end IoT solution, you have an edge device, you have a thing, it could be a sensor, an actuator, and then there's a cloud, right? So there are a variety of personas. There are developer personas, there are installer personas, there are managers, and then eventually the person who wants to use this application, right? So let's take a simple application of smart home where you have a Philips Hue, right? So can be Philips is the company which makes it available. So there's a developer persona inside that company, and then when it is packaged and shipped, someone buys it. It goes directly to the user, right? So there's a user persona, and inside the home there could be multiple users. There are capable users who know how to configure and manage the bulbs, light bulbs, through the Philips Hub and enable it on or Siri HomeKit, iPhone HomeKit, for example. So those are more capable guys who will at home enable it, but there are other users at home who just want to use it, right? So there are a variety of users and personas. In the field, for example, in the industrial setting, you can have a capability to monitor an industrial pump, vibration and life of a pump, right? So there will be guys who will go and pump. There will be other guys who will enable this pump for connected to the cloud or the edge node. So they will go and install. So those are the installer personas. They may not know how the solution works, but they will just do the installation. There may be other IT guys inside the organization who will do the installation of the software and or a third party install the software. So those installers would be there. Then there will be other OpEx guys who will manage the service, right? There will be other guys who will be managing the devices from remote, right? So those type of personas. Another question is, how are conflicts between different apps within separate containers managed? So there's a Docker Compose capability, talk about it, but that is typically used to manage the networking interfaces, the components, volumes, which can need to be shared between application components. So typically, if you want to keep all complete isolation between components, like for example, there is a pub sub MQTT broker I mentioned earlier. So that really talks about sockets. So on the networking interface, you enable socket and enable whatever port this application is going to use. And the other components of the application will use the same port to publish, for example. And that socket is available and communication will happen through those. So everything else will be isolated. So there won't be really any conflicts. Any guidelines when and how to introduce containers? It almost seems taking container approach is useful, and there are times when we should not go that route, right? So if you already have a solution deployed and you realize that the cost of managing the solution is high, the cost of updating the solution is high, and you're unable to scale, and then you want to move your components across different platforms, the components or capabilities across different platforms from the cloud to the fog or to the even the edge nodes. For example, analytics. So you are typically today doing analytics in the cloud and sending all the data to the cloud. So there's a cost of data storage in the cloud, the data to the cloud, and you're already, for example, deployed multiple of these edge nodes, and each of them is sending. And you may be in a scenario where you are on the same facility, same building, right? And so there are 10 connections, for example, from the rooftop, and each rooftop has 10 HVACs, for example, and each of them is connected. So you have 10 connections going to the cloud. Now you want to optimize this. These 10 nodes can be actually locally clustered, and you don't need cloud. You can probably have 1 or 2 connections going to the cloud. So the cost of sending data to the cloud will go down. And then you need to bring some of the analytics capabilities from the cloud to the edge now, because you have more compute. Clustering is kind of gives you that benefit of leveraging your compute at the edge. So you bring some of the analytics to the edge and reduce the amount of data going to the cloud. So when you want to do this, you want to really package your application, which was earlier, into microservices as containers and bring them to the edge. Next question is, I've tried Docker for Jules tools, or Docker engine first. That was not easy. Is there a Windows ClickNest installer yet? I think Docker install for Windows is probably self-contained. In fact, recently I did that for Pro on a NUC machine, and just download and click, did complete install of Docker framework. It even enabled Hyper-V on Windows, and I actually could run immediately with the PowerShell. So it is now pretty simple. If you go and look at one of the links I provided, getting started on Docker, you'll see that. I hope the link for the presentation is available soon. You guys will be able to access all the content, and there is a lot of embedded links in the content, hyper URLs in the content. So feel free to take benefit of my kind of research which I did on the web to get all the information, put it all together. This will help you build your solutions as containers, apps as containers, package them using Docker Compose, deploy them using Kubernetes, take advantage of these container tools, and build your end-to-end solutions which are scalable and happy scaling. So there's another question: does Intel provide any step-by-step guide or sample code to test it out? I think there is a lot of code available. Actually, if you see some of the links I have, they have in GitHub, so you can actually download Docker files really to build your containers. You can actually build native images. For example, there are ways to build grounds up image for the latest Ubuntu release, for example, or a lightweight Alpine distribution. You can build those images. A lot of information is available. Just Google. I think you'll be able to find. There would be some. I think the Joule SDK can be built as a Docker image inside a Docker image. So there are step-by-step. I think someone asked that question earlier. So there are steps to install Docker on your Windows platform. The Joule SDK can be built inside a Docker container, either on a Linux or on a Windows platform. There are steps for that. There is a lot of steps available. So there's, I would say, feel free to connect with me on a one-on-one, and I can kind of find some more information for you. Okay, so if there are no more questions, I'm going to end this session. Thanks for listening.